Okay, so let's talk about rational functions. So we're going to talk about the characteristics and how to find them algebraically. All right, then we're going to graph to kind of check our answers. Should be fun. All right, first let's do a little review. Rational functions have to do with polynomials. So let's review what a polynomial is. Right, a polynomial is just a sum of power functions and whose powers are non-negative integers. That just means positive whole numbers and zero. Right, zero is a non-negative integer. Right, so things like this: x squared minus 3x plus 1. The square, that's a positive integer. X to the power of 1 is a positive integer. And then this is really x to the 0 power, which is a non-negative integer. That's what they mean. So it's all these functions that we kind of been using all along, right? So 3x to the fourth plus 2x cubed, right? X squared, x to the first, and then the constant is really an x to the 0 power. So those are all non-negative integers. And one last one, right? We have a cube, a square, an x to the first, and again, a constant that has x to the 0. So those are all non-negative integers. All right. So just our normal kind of, I don't know, quadratics and things we've been talking about. Those are all polynomials. Okay. So non-negative integers. All right. So now a rational function is simply a function that can be written as a ratio of two polynomials. So we're going to have a polynomial in the numerator and a polynomial in the denominator. So like a p, well, the standard is r for rational, of course. And then p is used for the numerator one and q is used for the denominator one. Okay, and you'll notice we could have things like this, right? P could be this expression, and Q could be this expression. So there's going to be two polynomials, one the numerator, one the denominator. Okay, the only stipulations, right? We assume that Q is not a constant, so it has to have at least an X, right? And then also Q can't be zero, because if Q is zero, then that's undefined, right? Right. So those are our stipulations, but for the most part, it's just two polynomials, one in the numerator, one in the denominator. Okay. This is a nice example, right? So we have, here's a polynomial, 2x squared minus 3x plus 1, x cubed, x to the first plus 1. So that would be an example of a rational, all right? Okay, so we can have we will have characteristics of rationals. So since they're just polynomials, we can define the following. So if you want to find the x-intercepts, which are the zeros, then all you have to do is set the numerator equal to 0. Okay, and then after this, I'll show you why that is. All right, but we can define that. Well, if we want to find the y-intercepts, that's simply when the x is 0. So I substitute in 0 for here, which means I substitute in the 0 for all the x's over here, and I find what that y value is. Okay, we can also find the vertical asymptotes. There's a denominator. So if any of the x's produce zeros in the denominator, that will be a vertical asymptote. Okay, we have horizontal asymptotes. This is simply just end behavior. Right? This is when the function as x, what y does as x goes to positive, negative, infinity. Right? And remember, we'll evaluate these using limits. Okay. All right. And the last one's a slant asymptote. We're not going to get into that in this section or this video, but slant asymptotes are where the rational function actually goes to infinity, but it follows a line, right? And we can actually map out that line. Okay. One thing to note, and again, we'll talk about this later, but slant asymptotes always occur when the numerator power is 1 degree higher than the denominator. All right. Okay, so let's do our zeros. So first, why are zeros x-intercepts? Well, here's our rational function, right? So p divided by q. And remember, r of x is just function notation. Just treat it like a y. Well, how do we find a 0? A 0 is setting your equation equal to 0. So make y 0. Well, there you go. That's why it's an x-intercept. What is an x-intercept? An x-intercept is when y is 0. So if a 0 is found by turning the y to a 0, and that's what an x-intercept is, well, then they have to be the same. Okay? All right, so now let's look. So now what I want to do for x-intercepts and zeros is to solve this equation. Well, let's multiply both sides by q of x. And you'll see I'll get a 0 times q of x. Well, what's 0 times q of x? That's 0. So that's why all you have to do is set the numerator equal to 0 to find all the zeros. Right? And the zeros are x-intercepts. All right, so you don't have to go through the whole process. You can just kind of do the shortcut. All right. Okay, so you want to stop the video and complete classwork problem number 1. Okay, so let's find the zeros, the intercepts, and the asymptotes for this rational function, right? X plus 3 all divided by x minus 4. Right, so let's start with the X-intercepts. So remember, the zeros and the x-intercepts are the exact same thing. All right, so I'm going to set this equal to 0. And then if I do that, remember, I'll multiply x minus 4 to both sides. So really, it's just x plus 3 equals 0. Solve this. So when I plug in a negative 3, I will get a 0. So when x is negative 3, y is 0. And test it out. So negative 3 plus 3 is 0. Negative 3 minus 4 is negative 7. 0 divided by negative 7 is 0. All right, so it works out just fine. Okay, so let's do our y-intercept. So our y-intercept is when x is 0. So I want to find f of 0. So it's 0 plus 3 and 0 minus 4. So this will be a 3 divided by a negative 4, which is negative 3/4. So my my y-intercept is 0, comma, negative 3/4. All right. Okay, now let's do our asymptotes. So vertical asymptotes are when the denominator is 0. So let's take the denominator and just set it equal to 0. So solve this. I'll get x equals 4. That's my vertical asymptote. Now let's do horizontal. So horizontal is what happens to y as x goes to positive negative infinity. Well, that's limits. So I'll do the limit of this whole thing as x. And I'm going to do it all in one shot, and then I'll split it up because the simplification is the same. So it's the limit as I go to positive or negative infinity of this. Remember, since I'm going to infinity, the highest power dominates, and I just delete the rest. So I'll have an x over x, and then I'll simplify that to a 1. So I really want to find the limit of 1 as x goes to positive negative infinity. So this is suggesting that the y value is always 1. So the limit as x goes to negative infinity of 1 is 1 because it's always 1. The limit as x goes to positive infinity is 1 because it's always 1. All right, so that means the horizontal asymptote is y equals 1. All right, okay, so now let's check this. Let's plop up a graph and see if we're correct. So here's my function. I have an x-intercept of negative 3, 0, a y-intercept of 0, negative 3/4, a vertical asymptote of x equals 4, and a horizontal asymptote of y equals 1. All right, so let's graph this, use technology, and this is our graph. And you can see all 4 of those apply. My x-intercept is negative 3, 0. My y is 0, negative 0.75, which is 3/4. You can see I have a vertical asymptote, right? They go to infinity. The function goes off to infinity at x equals 4. And then it looks like it levels out to y equals 1. So we're good. All right, all good. Okay, so I want to stop the video. You want to complete classwork problem number 2. Okay, so the last thing we're going to do is sometimes we have functions that don't look like rational functions, and this is actually a rational function. So I want to rewrite this so it looks like two polynomials, the ratio of two polynomials. All right, so to do that, what we do is we get common denominators. So this is 1 over x plus 1. I need common denominators. So I put this x over 1 just to make it, look easy, or make it kind of line up. And then since the denominator is x plus 1, I'm going to multiply by a very clever 1 here, right? So it's like when we added 0, we can't multiply by a number other than 1 or we'll change what this is. So x over 1 times 1 is just x. So if I'm clever about my 1, I can change the way it looks and not change the equation. So that's why we've always, when we're doing common denominators, multiplied the piece by the same thing top and same thing bottom, because that really equals 1. Okay, all right, so I got my common denominators. Let's do our multiplication. I'll get x times x and x times 1. So I'll get a 1 over x plus 1 and an x squared plus x over x plus 1. And now I did all that work to get common denominators. Let's put them together. So you'll see this is x squared plus x plus 1, all divided by x plus 1. So this was a rational function. It just didn't look like it. All right, and what was the key here? We just got common denominators, that's all. Okay, so that's the end of the video. So you want to do classwork problem number 3.